The Second World War was not won by armies alone. It was won by the ability to build faster than the enemy could destroy. Guns, tanks, ships, and aircraft mattered, but behind each stood an even greater weapon, the assembly line. America's mastery of mass production turned factories into arsenals and workers into an industrial army. It was not genius or luck that overwhelmed the Axis, it was output. When war erupted in 1939, American industry was still recovering from depression. Within 2 years, it was transformed into the largest manufacturing system the world had ever seen. President Roosevelt's call to become the arsenal of democracy set the tone. Civilian car factories converted to tank and aircraft plants. Typewriter companies built machine guns. Refrigerator lines began stamping bomb casings. The country's industrial geography changed overnight. Detroit became the motor pool of war. Los Angeles became the heart of aviation. Pittsburgh poured steel for the world. The key to this transformation was standardization. Engineers designed machines, parts, and tools that could be mass-produced with interchangeable components. Each piece fit into every machine of its kind. The same principle that once made automobiles affordable now made tanks replaceable, rifles repairable, and aircraft buildable in the thousands. Production no longer depended on artisans but on systems. Factories became synchronized units of an industrial organism. Scale followed design. The Ford Motor Company's Willow Run plant built B-24 bombers using automotive methods. A bomber that once took 200 days to assemble could now be built in under 20. The plant stretched more than a mile, employing 40,000 workers and producing one bomber every hour at its peak. In shipyards, prefabricated sections of Liberty ships were welded together like toys. Airplane factories turned out thousands of fighters a month. This acceleration was powered by the integration of labor, machinery, and management. Workers were trained for narrow tasks. Machines repeated them endlessly. The human hand guided the machine guided the schedule, and the schedule guided the war. Women filled the factories as millions of men fought abroad. The image of Rosie the Riveter captured the spirit of total mobilization, an economy where every motion had purpose and every product was a bullet, a plane or a ration for victory. The industrial rhythm was relentless. Production lines operated 24 hours a day, 7 days a week. Government agencies coordinated materials, logistics, and wages. The War Production Board rationed steel, copper, and rubber. Engineers redesigned vehicles and weapons not for elegance but for speed of manufacture. Tanks lost ornamental features. Aircraft frames were simplified for quick assembly. Every design decision became a question of minutes saved and units produced. Efficiency itself became strategy. Numbers tell the story. By 1944, the United States was producing nearly half of all war materiel in the world. Over 300,000 aircraft, 100,000 tanks, and more than 2,000 warships were built within 4 years. What took other nations months to replace, America replaced weekly. Production outpaced destruction. It was not simply industrial power, it was industrial momentum, an unstoppable flow of material that buried the enemy under tonnage. But mass production was more than output. It was adaptation. Every new front brought new requirements. Desert filters for Africa, cold weather engines for Europe, reinforced hulls for the Pacific. Engineers redesigned machines faster than the enemy could learn from them. The same system that built automobiles now built evolution itself. Factories became laboratories where design met necessity in real time. The cost was discipline and fatigue. Workers endured endless shifts. Managers faced impossible quotas. Accidents, shortages, and strikes tested the system, but it never stopped. It could not stop. The industrial engine had become as vital as any battlefield. Generals measured victories not just in miles gained, but in machines delivered. When the war ended, the assembly lines that had built weapons began building peace. The same factories that produced bombers produced civilian airliners. Tank plants built tractors. The science of interchangeable parts and continuous flow became the foundation of modern industry. Mass production had proven that speed, organization, and volume could win wars. It was the invisible front, where machines built machines, and where victory was measured not in courage or strategy, but in output per hour. The industrial army of the home front never fired a shot, but it fired the world's greatest barrage of productivity. And in doing so, It redefined power, not as possession, but as production. Mass production during the war became a new form of warfare, one fought in factories, not trenches. Every assembly line was a front, every worker a soldier of steel and precision. The system's strength lay in repetition. A single perfected process could be multiplied across hundreds of plants. That meant thousands of identical engines, tens of thousands of rifles, and millions of rounds of ammunition flowing from one synchronized industrial organism. The United States had learned this logic decades earlier from Henry Ford's Model T assembly line. Now it was applied to everything from fighter planes to field rations. The goal was not craftsmanship but consistency. Engineers simplified designs, eliminating any part that slowed production. Welds replaced rivets. Bolts were standardized across vehicles and weapons. A mechanic in France could repair a tank built in Michigan using the same wrench as one repairing a truck in the Philippines. It was the standardization of the entire war. Factories learned to treat metal as material, not art. Components were stamped, pressed, and welded with mechanical rhythm. Conveyor belts carried unfinished planes past teams of workers, each performing one motion, then another, until an aircraft rolled out complete. The difference between war in 1914 and war in 1944 was not only technological, it was procedural. The machine had absorbed the craftsman. Training became industrial too. The U.S. government opened technical schools to train millions of workers in welding, machining, and assembly. Women filled those ranks in unprecedented numbers, running lathes and cranes with the same discipline once expected of soldiers. Posters and radio broadcasts turned factory labor into patriotic duty. Every rivet was a bullet, every finished engine another victory. The home front became the supply artery of the front line. Logistics matched production in complexity. Materials moved through rail networks, barges, and trucks in a constant loop. Steel from Pittsburgh became aircraft frames in California, ammunition in Illinois, and tanks in Detroit. Rubber, copper, and aluminum were rationed by government committees that functioned like military staffs. Nothing was wasted, nothing stood still. It was economy as mobilization, society as machinery. The results dwarfed imagination. Between 1942 and 1945, American shipyards launched more tonnage than all the Axis powers combined. Aircraft factories produced so many bombers that airfields had to expand just to store them. Tank assembly lines poured out armor faster than crews could be trained to drive it. The numbers were not just high, they were exponential. Production scaled with experience, efficiency feeding on itself until output became overwhelming. This overwhelming capacity forced strategic change. The Allies could fight prolonged campaigns because losses could be replaced instantly. A destroyed bomber squadron was rebuilt in weeks. Tanks lost in North Africa reappeared in Italy. Every setback on the battlefield was absorbed by the factory system behind it. Industrial resilience became military endurance, yet this system came at a cost. It demanded discipline bordering on regimentation. Workers labored long hours under fluorescent light, performing repetitive tasks without pause. The human body became another machine in the chain. Morale was maintained by propaganda, incentives, and the shared belief that production was survival. In that sense, the factory was both forge and front line, a place where patriotism met exhaustion. By 1945, the model had proven unassailable. America's wartime output exceeded that of Germany, Japan, and Italy combined. Industrial power had replaced manpower as the decisive element of warfare. The modern world's balance of power would forever rest not on armies in the field, but on factories at home. When the war drew to a close, mass production had not only won battles, it had rewritten the structure of civilization. The same methods that once built rifles and bombers now shaped the post-war world, defining everything from transportation to communication. The techniques of repetition, efficiency, and interchangeable design had become the new grammar of industry. America had proved that victory could be engineered. The home front's industrial mobilization had done more than supply armies. It had created a model for national organization. Every sector of society had been synchronized. Universities trained engineers for production. Scientists designed materials to fit factory needs. Government agencies managed resources with military precision. Even culture adapted. Radio programs, posters, and films all echoed the rhythm of the assembly line, teaching citizens that unity meant productivity. The war had mechanized not just labor, but belief. Factories that once turned out bombers began building civilian aircraft, cars, and appliances. The transition was seamless because the principle was the same: modular design, continuous flow, and standardized components. What had powered total war now powered total modernization. In a few years, industrial mass production created a new middle class, flooded markets with affordable goods, and transformed consumer expectation. The peacetime abundance of the late 1940s and 50s was the shadow of wartime mobilization. The military, too, never abandoned the system. The lessons of rapid scaling, supply coordination, and interchangeable design became permanent elements of defense strategy. The Cold War would depend as much on industrial potential as on nuclear arsenals. The concept of readiness itself came to mean the ability to produce quickly, in volume, and with precision. From aircraft carriers to missiles, mass production remained the heartbeat of military power. Culturally, it changed how people imagined war. The heroic image of the lone soldier gave way to the anonymous laborer, the unseen worker whose repetitive task built victory. The collective replaced the individual. Success was measured not in valor but in output. The idea that organization could defeat chaos, that structure could substitute for genius, became the modern creed. Yet the triumph was not without consequence. The same system that had given humanity control over production also distanced it from creation. Machines and processes began to define pace and purpose. People adapted to the rhythm of the assembly line, their work measured in speed and volume rather than craft. Efficiency became both virtue and burden. In historical terms, the war had industrialized modernity itself. It had proven that nations could convert abstract plans into material reality at astonishing speed, that will and machinery could merge into a single force. Factories had replaced fortresses. Blueprints had become as important as battle plans. The front line was no longer at the edge of an empire. It was wherever production began. By 1945, the lesson was clear. Control of production meant control of destiny. The Axis powers had fought with courage and strategy, but they had fought against an engine too vast to exhaust. Mass production had turned geography, manpower, and time into variables that could be managed by design. It was the first modern proof that power was not what a nation possessed. It was what a nation could make. The war ended, but the assembly line never stopped. Its sound became the hum of peace, the rhythm of cities, the heartbeat of progress. From tanks to tractors, bombers to airliners, the principle was the same. Repetition builds power, and power builds history. In the summer of 1939, a single letter changed the course of history. It was written by Albert Einstein and physicist Leo Szilard, warning President Roosevelt that recent discoveries in nuclear fission might allow Germany to build a new kind of bomb, one capable of destroying an entire city in a single blast. Within 3 years, that warning became the Manhattan Project, the largest scientific and industrial effort in human history. It would unite thousands of scientists, engineers, and soldiers in a race to harness the energy locked inside the atom, and it would end the war by redefining power itself. At its core, the Manhattan Project was an experiment in scale. It began as a theoretical question. Could uranium be split fast enough to sustain an explosive chain reaction? But theory quickly demanded industry. The U.S. Army Corps of Engineers under General Leslie Groves built secret cities to house laboratories and reactors. Oak Ridge in Tennessee enriched uranium, Hanford in Washington produced plutonium, and Los Alamos in New Mexico became the design center for the bomb itself. Entire towns were fenced, guarded, and erased from maps. More than 100,000 people worked behind locked gates, each knowing only a fragment of the whole. The scientific challenge was immense. Uranium existed in 2 isotopes, but only uranium-235 could sustain a chain reaction, and it made up less than 1% of natural ore. Separating it required massive electromagnetic and gaseous diffusion plants. At Hanford, reactors bred plutonium from uranium-238, creating an entirely new element, a metal that had never existed on Earth in significant quantity before the war. Each breakthrough demanded new physics, new engineering, and new courage. Every mistake risked contamination, explosion, or death. At Los Alamos, physicist J. Robert Oppenheimer assembled the greatest concentration of scientific talent ever gathered. Men like Fermi, Feynman, Teller, and Bohr. Their task was to turn invisible theory into a working weapon. Two designs emerged: a uranium bomb using simple gun-type assembly and a plutonium bomb requiring implosion by synchronized explosive lenses. Precision was absolute. The timing of detonators had to be perfect to within microseconds. The calculations were done by hand, by slide rule, by teams of women known as computers. Their work was the arithmetic of apocalypse. While the scientists labored in desert isolation, the factories behind them consumed resources on a continental scale. Oak Ridge alone used more electricity than New York City. Trains carried uranium ore from Africa and Canada under armed guard. Chemical companies built special materials to withstand the heat and radiation of new reactions. Every element of modern logistics, rail, power, chemistry, and computation, was absorbed into the single goal of release, the splitting of the atom. Secrecy was total. Few in government knew what was being built. To most workers, it was the gadget. Security clearances divided even the elite. Physicists were forbidden from discussing designs across groups. The isolation created an atmosphere of intense focus and growing moral unease. As the weapon took shape, its builders began to understand that they were creating something beyond all precedent, a force that could destroy civilization as easily as it could end the war. On July 16, 1945, the desert of New Mexico turned to light. The first atomic explosion, codenamed Trinity, vaporized the sand into glass and sent a shockwave felt 100 miles away. Oppenheimer watched through darkened goggles and recalled a line from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." The equation had worked. Humanity had split the atom, and with it, its own innocence. 3 weeks later, 2 bombs ended the war. Little Boy fell on Hiroshima on August 6th, Fat Man on Nagasaki 3 days later. Over 100,000 people died instantly, and many more in the weeks that followed. Japan surrendered. The Manhattan Project had achieved its purpose, but at a cost no one could measure. The weapon had ended one war and begun a new one, the Cold War, an age of perpetual atomic tension. The project's legacy reached far beyond the battlefield. It transformed science into a branch of state power. The fusion of government funding, military organization, and scientific research became the model for all later technological programs, from nuclear energy to space exploration. It also redefined the ethics of discovery. The same minds that had unlocked the atom now struggled with the question of whether knowledge itself could be too powerful to control. In the years after the war, the laboratories at Los Alamos and Hanford became the foundations of the nuclear age. Reactors that once bred plutonium now generated electricity. The same chain reactions that destroyed cities now lit them. Yet the shadow of the Manhattan Project never faded. It proved that science could command forces once reserved for gods, and that once created, those forces could never be undone. The Manhattan Project was the ultimate expression of the 20th century's faith in progress, and its greatest warning. It showed that reason could conquer nature, but not necessarily control the consequences. It was both triumph and tragedy, the moment humanity realized it could end war, or end itself. The Manhattan Project's power lay not only in its physics, but in its organization. It was the first time science, industry, and the military operated as one. General Leslie Groves managed the project with the precision of an army campaign, while Oppenheimer led its intellectual front. Together they created a new model for warfare, one where equations and logistics mattered as much as tactics and courage. The system Groves built was staggering in scope. Oak Ridge, Hanford, and Los Alamos were not laboratories but entire cities, built from nothing in months. Oak Ridge spread across 60,000 acres of Tennessee hills, its miles of power lines feeding the vast electromagnetic separators known as calutrons. These machines isolated uranium-235 atom by atom, consuming enormous energy. Hanford, hidden along the Columbia River, operated nuclear reactors that bred plutonium inside uranium fuel rods. Workers handled materials they barely understood under layers of secrecy and radiation shielding. At Los Alamos, the intellectual heart of the project, Physicists converted that material into weapons of precise geometry and unimaginable force. The logistics of secrecy rivaled the engineering. Mail was censored. Telephones were monitored. Scientists were forbidden from leaving without permission. Even their families lived under coded addresses. Most of the 125,000 workers never knew what they were making. They refined uranium, welded casings, assembled circuits, each task a fragment of a puzzle known only to a handful of men in a desert laboratory. Inside that laboratory, the science moved at the edge of possibility. To trigger a chain reaction, fissile material had to reach a critical mass in microseconds. The uranium bomb, Little Boy, used a simple gun-type mechanism that fired one subcritical mass into another. But plutonium, created at Hanford, behaved differently. It emitted spontaneous neutrons that could cause premature detonation. The solution was implosion, compressing a plutonium core inward with synchronized explosive charges to reach supercritical density. The challenge was synchronization. Detonators had to fire within millionths of a second of each other. This required new mathematics, new materials, and new precision tools. Metallurgists learned to shape plutonium without cracking it. Explosives experts built lenses of varying density to bend shockwaves uniformly. Engineers invented fast electronic circuits capable of timing with unheard-of accuracy. The entire process was a lesson in controlled chaos, theory converted into machinery at the edge of what humans could measure or imagine. Oppenheimer's leadership gave the chaos order. He fused physicists, chemists, and military officers into a single working unit. Arguments were frequent, failures constant, but progress never stopped. At night, scientists debated quantum mechanics in the dining halls. By day, they tested explosives in the desert canyons, measuring flashes with high-speed cameras. Every breakthrough led to a new crisis, and every crisis drove invention. The bomb was not built in a straight line. It was wrestled into existence by intellect and urgency. Parallel to the science, moral unease grew. Many of the physicists were refugees from Europe who had fled the Nazi regime. They feared that Germany was racing toward the same goal. But by 1944, when evidence showed that Germany's nuclear program had failed, their motivation shifted. They were no longer preventing a German bomb. They were creating an American one. Some urged restraint. Others believed that only demonstration through use could justify the cost. No one yet understood how absolute the weapon's power would be. By mid-1945, the project had consumed $2 billion, more than any single engineering effort in history. It had mined continents, built factories the size of cities, and generated technologies that would define the next century. Yet it all narrowed to one point: a small metal sphere, no larger than a basketball, waiting in the desert to prove whether humanity could command the atom or be consumed by it. The scientists called it simply the gadget. Its detonation at Trinity would test not only their equations, but their faith in knowledge itself. The success of that single blast would signal that mankind had crossed a threshold, from discovering nature's laws to rewriting them. At dawn on July 16, 1945, the desert at Alamogordo, New Mexico, became the proving ground of human intellect and consequence. The bomb stood on a steel tower, its core of plutonium surrounded by lenses of high explosive wired with perfect symmetry. At 5:29 a.m., the countdown reached 0. A light brighter than the sun tore through the sky, followed by a wave of heat that turned sand to glass and shook the mountains. The first atomic explosion, Trinity, had worked. The equations were real. In the control bunker, silence fell. For seconds no one spoke. Oppenheimer's mind reached back to the Bhagavad Gita. Now I am become death, the destroyer of worlds. Others cheered, some wept, some stood still, unable to grasp what they had seen. The blast yielded about 20 kilotons of TNT, a number that meant little compared to the reality it represented. The desert glowed with its own sunrise. Humanity had entered the atomic age. Within weeks, the weapons built from that experiment were prepared for use. On August 6th, Little Boy, the uranium bomb, was dropped on Hiroshima. 3 days later, Fat Man, the plutonium bomb, fell on Nagasaki. Both cities were erased within moments. The heat incinerated buildings, vaporized human beings, and left radiation lingering in the air. Over 100,000 lives vanished in seconds. Japan surrendered soon after. The war that had consumed the world ended, not with armies meeting in battle, but with a single detonation. The Manhattan Project had achieved its purpose, but its success carried a burden. The same science that had liberated the world from fascism had also shown how easily civilization could destroy itself. Many of the project's scientists were shaken. Some resigned, others turned to advocacy, warning of a future where war would mean annihilation. The weapon they had built was no longer a secret. It was a precedent. In its shadow, a new kind of war began. One fought not for territory, but for survival. The legacy of the Manhattan Project extended far beyond Hiroshima and Nagasaki. It had fused government, science, and industry into a single mechanism of creation and control. Its laboratories became the seed of the Cold War's atomic complex. Los Alamos, Hanford, and Oak Ridge continued producing nuclear materials for bombs, but also reactors for power and research. The project's organization became the model for future national programs: the hydrogen bomb, the space race, and the development of computing. Technologically, the project pushed the boundaries of every field it touched. Reactor design, metallurgy, chemistry, electronics, all advanced decades in just a few years. The need for fast calculations spurred early work on digital computers. The precision machining of nuclear cores led to new standards in measurement. Nuclear physics itself became an instrument of policy. Knowledge had become a strategic resource. But beyond the science, the moral dimension of the Manhattan Project defined the rest of the century. It forced humanity to confront a question it had never faced before, not whether it could build something, but whether it should. Power and destruction had become identical. Every invention that followed would carry the same question in its shadow. Oppenheimer, once the architect of the bomb, became its conscience. He warned that the weapon's success had turned science into sin. In 1954, he was stripped of his security clearance, a symbol of the new tension between knowledge and authority. Yet his creation remained. The world's balance of power now rested on fission, a fragile peace enforced by fear. In the end, the Manhattan Project was not only the end of one war, but the beginning of a new era. It proved that the mind could master nature at its deepest level, and that mastery was irreversible. From the light of Trinity to the fire over Hiroshima, it marked the moment humanity stepped across a threshold it could never recross. The bomb was not just a weapon, it was a mirror. In its reflection, humanity saw both its genius and its peril, and learned that the cost of ultimate knowledge is never fully known until after it is paid.